Hello everyone, welcome to David Griffiths Electrodynamics. This is going to be problem 4.21 from the book. As always, if you're new, welcome, and if you're returning subscriber, welcome back. Be sure to leave a like, comment, subscribe on the video, check out the membership options for the channel. And other than that, let's get started. So, problem 4.21 states that we have a coaxial cable that consists of a copper wire, which is a radius of A, and then it's surrounded by a concentric copper tube of inner radius C, and the space between is partially filled from B out to C with the material of dielectric constant epsilon R as shown. So, and then it wants us to find the capacitance per unit length of this cable. So we have this like copper wire that's radius of A, and then from A to B there's like empty space. Then from B to C we have like a tube that is filled with some dielectric constant, linear dielectric with a dielectric constant of epsilon R. And our goal is to find the capacitance per unit length of this cable. So let's move to this view. All right, so I kind of redrew the diagram here. We have our different radiuses of the different shells. We have our dielectric constant that fills this space. And of course we know the capacitance of this is essentially a capacitor. It's a cylindrical capacitor, not a parallel plate capacitor, but we know the capacitance is given by this relation, the charge per potential difference, Q over V. So we're just going to let Q be the charge that's on, pretend we don't know how, it doesn't tell us how long this cable is, but let's just say we have some cable of length L. And so this is like going into the page, right? We're looking at a cross section of the cable, but you can imagine this cable runs for some length L. So Q is just the total charge on our capacitor, or on our capacitor here. Then what we need to find is the potential that's at the various regions. And to do the potential, we're going to need to know the electric field at the various regions. So the regions we care about are going to be the electric field from, inside of our copper wire, it's a conductor, so there is no electric field inside of, less than A. But between A and B, there should be some electric field. And then from B to C, there should be a slightly different electric field because of the dielectric. So we need to find those electric fields. And we can do that by using Gauss's law, but we know that there is, we know the free charge that's on the conductor or in the cable is Q, right? So we can use Gauss's law for the displacement field that only relates to the free charge to figure this out. So the flux of the displacement field is equal to the enclosed free charge. And for the region S, and our Gaussian surface is going to be a cylindrical Gaussian surface because of cylindrical symmetry happening here. So for the radius B to C, our Gaussian surface is going to be some cylinder that has a radius between B and C that kind of runs along and encompasses. It should encompass most of the material, but not quite all of it, obviously. All of the charge should live. All the free charge should live on the conducting material, so it should encompass all of the free charge that lives on the conducting copper wire. So the right side of Gauss's law should just be Q, which is all of the charge. But the left side, of course, is just going to be, D is going to be a constant for across our Gaussian surface, and then the surface area of our Gaussian surface is 2 pi s times the length of our cable L. Solving for D, then we get Q over 2 pi SL. And then the electric field then is the displacement field over the dielectric over this E So we just divide by epsilon here, and this is going to be our field for the region B to C. And then in the region A to B, where we have a vacuum, that epsilon is just going to be replaced with epsilon naught. You could do the exact same argument here. You're just going to replace epsilon. When you do this, right, D is going to be this, but epsilon is epsilon naught, epsilon r, but the dielectric constant of a vacuum is 1, so you just have epsilon naught. So then you get epsilon naught on the bottom. So this is the field then between the regions A and B. So then to figure out the potential across our entire capacitor, we got to go from C to A. We got to do the negative line integral from C to A of E dot dl. So we split this into 2 line integrals. We go from C to B, or I start from the outer shell to go into the inner, but you could also go from the inner to the outer, which I think is what Griffiths does, but I'm just doing it this way. So minus integral from C to B of the electric field between C and B, which is Q over 2 pi L epsilon 1 over S ds, minus the line integral from B to A, the second section, of Q over 2 pi L epsilon naught 1 over S ds, right? And dl is just going to be the radial cylindrical coordinate. So, and we know that the electric field is going to only be radial in this case, just from symmetry. So that's why we just get the dot product just gives us that component. So all we're integrating here is 1 over S ds, and so what function has a derivative of 1 over S essentially, and that's the natural log function. So this is just a standard integral. So what we end up getting is the integral 1 over S is the natural log of S evaluated at the 2 bounds. So what you end up getting is, like, for this case, you get natural log of B minus the natural log of C, which then the natural log of B, like the natural log of A minus the natural log of B is the natural log of A over B. So you can use that relation. So this becomes a natural log of B over C. And we still have this minus sign here. And we have minus, all the constants times the natural log of A over B for this one. And then it just becomes a matter of taking out terms. So we factor out all of our constants, Q over 2 pi L. We have 1 over epsilon natural log of B over C plus 1 over epsilon naught natural log of A over B. Then because epsilon is epsilon naught epsilon r, we can then factor out a common factor 1 over epsilon naught. So then this term, we bring out a 1 over epsilon naught, and then this term I swap to the front, and we just have natural log of A over B plus 1 over epsilon r natural log of B over C. And so with a minus sign out front. So this is going to be our term we use for the potential. So then to find the capacitance per unit length, that's just going to be C divided by L. So that's going to be Q over V, which is the capacitance divided by L. So we just plug in our potential that we just found. So we have a minus sign, we have a Q here, and then when you do plug in 1 over V, you got to flip all of this. So you end up getting the 2 pi epsilon naught L on top, then you get the Q on the bottom, and then you get that natural log stuff on the bottom here. And I should have wrote like this, hang on. There's an L on the bottom from here. So the L's cancel, the Q's cancel, and you just get a minus 2 pi epsilon naught divided by the natural log of A over B plus 1 over the dielectric constant times the natural log of B over C. And I think what Griffiths ends up getting is he flips the natural logs, so he goes B over A and C over B because he did his potential from the center out rather than from out to the center. So he gets the same potential, but it's like flipped by a sign essentially, which makes sense. But anyways, I just did it this way, so we have a minus sign here compared to what Griffiths has, and his natural logs are flipped around. But this should be the same. So the capacitance per unit length is given by this expression here. All right, if this video helps you guys out, feel free to let me know. Leave a like on the video, subscribe to my channel if you haven't already, check out those membership options as well. But as always, thank you guys for watching, and I'll see you guys on the next video.